In this lecture, we will apply the theory of absorption to the Streeter-Phelps model and review the concepts used in creating DO-sag curves.
Okay, what I am going to do next is move into an example of where we use this concept of Fick's law adsorption of gases to model water quality. Now, back in 280, you did a little bit of this. However, you may not remember. And go through this a little bit, maybe a little bit more detail in terms of the assumptions versus what was done in 280. So we're looking at predicting river quality. So think about this as we have a river, we have an outfall. So let's say from the wastewater treatment plant. We have the biochemical oxygen demand in the wastewater. We have the dissolved oxygen in the wastewater. We have the BOD upstream from the outfall, so river flow in this direction. We have a dissolved oxygen upstream. We can calculate the BOD downstream and the dissolved oxygen downstream. So we will typically model this as, this is our control volume. We'll assume that we have complete mixing. And when we do this, we can write an expression that the dissolved oxygen upstream times the BOD upstream plus the BOD in the wastewater times the dissolved oxygen in the wastewater is equal to the dissolved oxygen downstream times the BOD downstream. Now I've made some assumptions. Got mass balance. What are the assumptions I've made? Mass balance, okay. Continuous mixing. So we've got a CSTR. I've made the assumption that the change in mass with respect to time is equal to 0. Assumption then is, okay, I'm assuming flow in equals flow out. Okay, good. So Q downstream equals Q up plus Q wastewater. So we have no loss of flow. But if I assume that the change in mass with respect to time is equal to 0, what is that referred to as? Steady state. We'll also assume, notice there's no reaction term. So we're assuming the chemical is conservative. We'll assume that the flow of the wastewater is continuous. So it's just not, okay, so we have continuous flow in, out, it's not changing. The basis of what we do in terms of predicting river quality, and we use the Streeter-Phelps equation, is based on this premise. Okay? So we're going to model that input as a CSTR. And we have an example here. We've done similar problems that we've done, okay, where we have a river. We have a flow in the river of 0.991 meters cubed per second equals Q. We have wastewater entering the river, and the Q of the wastewater is equal to 0.526 meters cubed per second. Just upstream, so this is, we'll call this up, the BOD is equal to 6.2 milligrams per liter, and the BOD in the wastewater is equal to 30.1 milligrams per liter. So we will do the same. We've got our control volume. What we're looking for is the BOD downstream. And that is simply 0.991 meters cubed per second times the BOD upstream plus the flow in our wastewater, 0.526 meters cubed per second, times the BOD in the wastewater, and that is equal to the total flows. We can add up our flows. Okay, and we're looking for the BOD downstream. And that is simply then equal to 14.5 milligrams per liter. So that's the BOD down. We need to know that because what we're modeling then is in here, this parcel, we have a concentration of BOD equal to 14.5 milligrams per liter. So we're looking at what happens as that parcel moves downstream. Okay, so BOD, biochemical oxygen demand. It's the amount, wrote it before for the iron reaction. It's inorganic, but we can think about it that way. Okay. It takes oxygen. Actually, let's write it for an organic. So we have glucose, C6H12O6. Reacts with oxygen to produce CO2 plus water. Okay. We have 6 oxygens, so we're going to produce 6 CO2s. We have 12 hydrogens, so we need 12 here. And now, well, let's see, we've got 6 oxygens and 12 oxygens, so we need 6, okay? So for a given concentration of glucose, we can calculate how much oxygen is needed. And that's based on the stoichiometry, that's the theoretical oxygen demand. Now, if we take that, let's say, 5 milligram per liter glucose solution, and we put it into a bottle, we add microorganisms, we can calculate how much oxygen the microorganisms use up, and that's our BOD. So as this parcel moves downstream, what can happen? And think of it just in terms of glucose. What can happen to that parcel? So the parcel's moving downstream. What can happen to that parcel as it moves downstream? It can be agitated. And if it's agitated, what's going to happen in terms of the oxygen? Okay, it's agitated. If we get agitation, we get mixing. We get reaeration. What else can happen? Do we have microorganisms in the water? Yes. So what else can happen? Think of it in terms of glucose. Microorganisms can use the glucose, so we get decomposition. So basically, we have 2 different reactions here. We have a decomposition reaction, and we have a reaeration reaction. So in terms of modeling the behavior or the water quality, we need to look and we need to be able to model both reaeration, Fick's law, and decomposition. We will use the Streeter-Phelps equation, also known as the Diosat curve equation. So we're looking at the decomposition of the chemical or the removal of oxygen by the microorganisms as they're biodegrading that chemical. We'll also look at reaeration. So we'll look at adding oxygen back into the system because of reaeration. We will also make some assumptions. So we will assume that the concentration in our wastewater is constant with time. The time that we're looking at, we don't have any change. We will assume that the flow of wastewater is also constant with time. We talked about mixing. So in that control volume, where we have input, okay, we'll assume that we have steady state and no reaction. So it's conservative. So that's in when we're adding. We will also assume that, so here's our river. We have this control volume. We will assume that in the control volume, we also have complete mixing. Concentration's constant across the river, and it's just moving down the river. So that parcel is moving down the river. Because we're assuming that, we can assume we have plug flow conditions. The other thing that we will assume or we'll use in these is we'll use the BOD ultimate. You may remember back from 280, typically we measure a 5-day BOD. If you go back and think about the glucose, and we're modeling this as BOD versus time, it takes time for the microorganisms to degrade that glucose. Well, and it's an exponential curve. If this is 5 days, this is our BOD 5. However, if we give the organisms enough time, then they'll keep degrading that glucose, and eventually it's completely degraded and we have the BOD ultimate. Okay. In the model, we will typically model this as L naught. So this is just a typical diagram showing the Streeter-Phelps model. So we have some discharge, okay, and we can, prior to the discharge, we've got a constant dissolved oxygen concentration. We have discharge, and now the microorganisms are consuming the organic material, degrading that material, consuming oxygen until a point where the rate of reaeration is equal to the rate of decomposition. Once reaeration predominates, the river starts to recover, and eventually the dissolved oxygen reaches a much more constant value, could potentially reach saturation. Okay, there's enough reaeration. At the same time this is happening, the biochemical oxygen demand is decreasing. We're using up that organic that's being consumed, it's being degraded. And once that's completely consumed, then reaeration controls the process. As mentioned, the mathematical model of the decay of dissolved oxygen levels in a stream, so the Streeter-Phelps model, is dependent on both the rate of deoxygenation and the rate of reaeration. So we can describe the rate of deoxygenation as equal to the rate constant times the amount of BOD remaining at any time t. The rate of deoxygenation is then equal to KD times L naught e to the minus k dt. Note, this is because, again, if we plot the BOD as a function of time, that BOD will increase as the organisms consume more of that material. They're consuming more oxygen, and eventually it will reach what we refer to as the ultimate BOD, which we often describe as L naught. Okay, so that is the ultimate BOD. And the ultimate BOD is what we use in the DOSAG curves because we want to know how much oxygen can be consumed, and we're looking at that over a significant period of time. The deoxygenation rate constant needs to be adjusted for temperature. As you can imagine, metabolic activity is dependent on temperature, and we have two different theta values for temperatures between 4 and 20 degrees and temperatures between 21 and 30 degrees, and the screenshot is actually from the FE reference handbook. So note, as you might expect, as the temperature increases, the deoxygenation rate constant also increases, metabolic activity increases. We can also look at the rate of deoxygenation and how the deoxygenation constant and how that relates to stream qualities. So for example, the BOD rate constant and the deoxygenation rate constants are approximately equal for deep, slow-moving streams. However, for shallow, turbulent, rapidly moving streams, we can relate the deoxygenation constant to the BOD rate constant using this equation here. So K is the BOD rate constant plus V, the velocity of the stream, divided by the average depth of the stream times the bed activity coefficient. And the bed activity coefficient also relates to the quality of the stream, and it ranges from about 0.1 for relatively stagnant or deep water to 0.6 for rapidly flowing water. Now, as I mentioned, the model is really the sum of deoxygenation and reaeration. So we need to talk about how to model the reaeration of oxygen back into the stream. And we've talked about this previously, but if you can imagine, the more rapidly moving the stream, the more turbulent the stream, the greater the rate of reaeration. So if you think about the red cedar, it's going to have much more reaeration in the area around the rapids by the admin building versus an area of the stream that is much more slow moving. So the rate at which oxygen is transferred from the air is based on Fick's law, and we can write an expression that the change in oxygen as a function of time is equal to Kr, the reaeration concentration, times the difference in the DO saturation concentration and the DO, the dissolved oxygen concentration at that particular time. And note, this term here is what we refer to as the deficit. So this is equivalent to K sub R times D, where D is the deficit. And this is important because you'll see that in the Streeter-Phelps model, the term that we use for dissolved oxygen is not the dissolved oxygen concentration, but the deficit. The reaeration rate constant is dependent also on the physical characteristics of the stream. And we can write that the reaeration constant is equal to, and this is an empirical expression, 3.9 V to the 0.5 times H to the 1.5 power. Note the units. This is important. Okay. As I mentioned, this is an empirical equation. So it was derived with units of meters per second. And notice that the power functions are different. So it's important to make sure that you're using units of meters per second. And the values of reaeration constants range from about 0.1 for small quiescent ponds to greater than 1.5 for rapids and waterfalls. And note, this is in units of inverse days. We also need to readjust the reaeration constant as a function of temperature. We use the same equation from the FA reference handbook. However, in this case, the theta value is 1.024 and is not dependent on temperature. We can also adjust the dissolved oxygen saturation concentration for salinity and temperature. And the DO sat is equal to 475 minus 2.65 times the total dissolved solids. Notice that's in grams per liter, divided by 33.5 plus T minus 273. Notice T is in Kelvin. So make sure you're using the proper units here. And this will allow you to adjust your DO-sat level for TDS and for temperature. Get to the Streeter-Phelps model. Notice we're modeling the change in concentration. It's the change in dissolved oxygen concentration as a function of time. Notice here, again, we have the deficit. Okay? So we have a term for reaeration, and we have a term for deoxygenation. And if we integrate this expression as a function of from C naught to C and as a function of time, we can develop an equation for the deficit. So remember, again, this is the deficit. The equation is straight out of the FA reference handbook. This L sub A is L sub naught that I used before. So this is your initial BOD just after mixing, and this is the initial deficit. Okay. And we have deoxygenation terms throughout and reaeration terms. We often talk about what is referred to as the critical point. So that is the point where the deficit is the maximum. So if you remember, we said this is the point where the rate of reaeration is equal to the rate of deoxygenation. So at this point in time, the deficit is a maximum and the dissolved oxygen concentration is a minimum. The only difference in that equation, okay, is that we're using that T is T critical. So we can calculate the critical time using this equation, and then the critical deficit simply becomes the previous equation where we have KD L sub A divided by KR minus KD e to the minus KD over T times T sub C minus e to the minus KR times T sub C plus D sub A e to the minus KR times T sub C. So let's look at this problem here, where we have a uniform natural stream. Given the depth of the stream, you're told the velocity of the stream. You're told that the stream contains oxygen-demanding substances, so it has BOD, and they decay and utilize oxygen according to a first-order kinetics. So just below the outfall from a wastewater treatment plant, the ultimate BOD is 25 milligrams per liter, and the dissolved oxygen is 4.1 milligrams per liter. The temperature is 25 degrees C. So let's just kind of start that out, and we'll draw our stream here. We have a outfall from a wastewater treatment plant, and just below the outfall, so we've taken into account mixing, the ultimate BOD, remember that is equal to L naught, and you'll see it also designated as L sub A, is 25 milligrams per liter. The dissolved oxygen is 4.1 milligrams per liter. The temperature is 25 degrees C. The saturation dissolved oxygen concentration at 20 the saturation dissolved oxygen concentration is 8.38 milligrams per liter. So this is our DO set, and that is equal to 8.38 milligrams per liter. You're given the KD for the stream, so the deoxygenation rate constant. That was determined though at 20 degrees C, and you're told that the TDS of the stream is 500 milligrams per liter.
And we're asked to determine the critical DO, the critical distance, and the dissolved oxygen concentration 16 kilometers downstream.
Now notice this DO set is for pure water. Okay, so just to remind you of that. So again, let's just write down the information that we know. So we know our ultimate BOD is 25 milligrams per liter. We'll designate that as L naught, and also you'll see it as L sub A. And it really just depends on the notation in the Streeter-Phelps equation. The dissolved oxygen concentration is 4.1 milligrams per liter. You said temperature is 25 degrees C. Saturation DO is 8.38 milligrams per liter. This is, remember, this is for pure water. We were told that the TDS is equal to 500 milligrams per liter, and that's equal to 0.5 grams per liter. Remember, we need to, if we're going to use that equation to calculate the DO sat, then we need to have that in grams per liter. And we're told that KD is equal to 0.31 inverse days, KR is equal to 0.76 inverse days, and both of those are determined at 20. We need to adjust both of those values for temperature, and KT is equal to K at 20 degrees, theta T minus 20. And for reaeration, theta is equal to 1.024. Our reaeration constant is equal to 0.76 inverse days times 1.024 25 minus 20. And that is equal to 0.85 inverse days. The deoxygenation rate constant also needs to be adjusted. And in the temperature region we're looking at, theta is equal to 1.056. So the deoxygenation constant is equal to 0.31 inverse days times 1.056 to the 25 minus 20 power, and that is equal to 0.407 inverse days. We can calculate the DO sat using the equation that I previously gave you as 475 minus 2.65 times 0.5 grams per liter divided by 33.5 plus 273 plus 25 minus 273, and that is equal to 8.097 milligrams per liter. So we'll use that as our DO sat because that took into account not only temperature, but also takes into account the TDS in the water. So the critical time, which is what we were asked to determine, is equal to 1 over KR minus KD ln of KR minus KD 1 minus D sub A times KR minus KD divided by KD L sub A. And that is equal to 1 minus our 0.85 minus 0.407 ln of 0.85 divided by 0.407. 1 minus, now we need the deficit. Let's just write that over here. So our deficit is equal to 8.097 minus the 4.1. So that is equal to 3.997 milligrams per liter. So that's 3.997 times 0.85 minus 0.407. And then that is divided by 0.41 KD, or 0.407, times 25 milligrams per liter. And that is equal to 1.23 days. So if we think about this, this is our deficit versus time. This is going to decrease until the point where the stream has moved, or that packet has traveled the equivalent of 1.23 days. Now we were given the velocity in the stream, so we could actually calculate the distance. So that's 1.23 days times the velocity we were given was 0.4 meters per second. Let's multiply that by 86,400 seconds per day. And we'll times 1,000 meters per kilometer. So meters cancel, where seconds cancel, days cancel, and what we will have is the distance downstream, and that is equal to 42.5 kilometers. So this distance here, okay, that parcel of water has to travel 42.5 kilometers, okay, or 42.5 kilometers downstream, we'll see the maximum deficit or the minimum DO. Now that we've calculated the critical time, which we said was 1.23 days, we can calculate the critical deficit and then the dissolved oxygen at this critical time. So to calculate the critical deficit, that is simply KD times L sub A divided by KR minus KD, E to the minus KD times T sub C minus E to the minus KR times T sub C plus the initial deficit E to the minus KR, again, times T sub C. So if we substitute in, we have 0.41 inverse days times the initial BOD, 25 milligrams per liter, divided by 0.85 minus 0.41 inverse days times E to the minus 0.41, that's inverse days, times 1.23 days, minus E to the minus 0.85 inverse days, times 1.23 days, plus the initial deficit, which is 8.097 minus 4.1 milligrams per liter, times E to the minus 0.85, and that's inverse days, times 1.23 days. And calculating the deficit is 7.25 milligrams per liter, and the DO at the critical time is equal to 8.097 minus 7.25 milligrams per liter, or 0.84 milligrams per liter.
Let's draw another graph of their dissolved oxygen or deficit concentrations. So we've plotted deficit versus time, and you can see how that decreases over time. And we have a concentration of 8.4 milligrams per liter at a travel time of 1.23 days. And we can also look at the deficit, and shown here is the deficit at 7.25 milligrams per liter, and that's assuming that the river is at 8.097 milligrams per liter saturation. The last part of this problem is to calculate the dissolved oxygen concentration at 16 kilometers. Note, we just calculated the critical time of 1.23 days, which was associated with 42.5 kilometers downstream from the outfall. In order to do this, we need to calculate the time that it takes to travel 16 kilometers downstream. So it takes 16 kilometers. We need to convert to meters. So 1,000 meters per kilometer. We'll divide that by the velocity, 0.4 meters per second, and then multiply by 86,400 seconds per day. And note seconds cancel, kilometers cancel, meters cancel, and we're left with days. 0.46 days is the travel time that it takes for that water to move 16 kilometers downstream. Now calculate the deficit using the same equation that we did so before. So the deficit is equal to 0.41 inverse days times 25 milligrams per liter divided by the reaeration constant, 0.85 inverse days minus 0.41 inverse days, the deoxygenation constant, times e to the minus 0.41 times 0.46 days minus e to the minus 0.85 inverse days, again times 0.46 days, plus the deficit, 8.097 milligrams per liter minus 4.1 milligrams per liter times e to the minus 8.5 inverse days times 0.46 days. And that is equal to 6.22 milligrams per liter. So that is the deficit. And the dissolved oxygen concentration is equal to the saturation concentration, 8.97 milligrams per liter minus 6.22 milligrams per liter. That's equal to 1.87 milligrams per liter. Looking back at the graph that we previously drew, we can add a travel time of 0.6 days and the deficit of 1.87 milligrams per liter. And finally, we see at the critical deficit, the rate of reaeration is equal to the rate of deoxygenation, and at distances greater than that associated time or distance, the rate of reaeration starts to dominate over the rate of deoxygenation. So from this video, you should be able to explain the theoretical basis of the Streeter-Phelps model, calculate the critical time and deficit, and also calculate the dissolved oxygen concentration as a function of time using the Streeter-Phelps model.